The environmental, social, and economic consequences of global warming are becoming increasingly apparent. Human activities from pollution to overpopulation are driving up the Earth's temperature and fundamentally changing the world around us. Transitioning to renewable energy is one of the key ways of reducing carbon emissions, and society is transitioning more and more each day. However, we must ensure there is a diverse mix of renewable sources to guarantee consistent and reliable energy for all. The next challenge and frontier in a decarbonized world is ocean renewable energy. There is enormous potential for ocean renewable energy. The potential kinetic energy in waves is huge. Wave energy could contribute 10% of Australia's energy needs. Achieving this potential calls for innovative solutions to make ocean renewable energy cost competitive at commercial scales. This film showcases 5 young researchers from the Wave Energy Research Centre at the University of Western Australia. They are undertaking cutting-edge research to be a part of the solution to one of the most significant issues of our time. The Wave Energy Research Centre is a multidisciplinary team of over 30 researchers located at the University of Western Australia, with nodes in Albany in the south and Perth on the west coast of Western Australia. Established in 2018, the centre is a knowledge hub for academics, industry, and the community to drive development of the ocean energy sector. Its research and fieldwork activities span across physical oceanography, hydrodynamics, and environmental and geotechnical engineering. They leverage expertise built over the past 3 decades in ocean engineering at UWA through the collaboration of a wide range of domestic and international stakeholders. These activities are designed in a surface-to-seabed approach with 3 main research programs: coastal processes, wave device interaction, and foundation design. Program 1: Coastal Processes. Program 1 observes and characterizes the wave and current conditions necessary to successfully deploy wave energy converters. Understanding offshore and nearshore physical processes is critical for determining an optimal location for a wave energy installation. These analyses also take into account the potential impacts of wave energy farms on the coastline. The following 2 PhD research students are part of Program 1 and will describe their projects in more detail.
Hi, I'm Carly Porch and I am a 3rd-year coastal engineering PhD student at the Wave Energy Research Centre. Previous to this, I completed my undergraduate degree in civil engineering at Queen's University in Ontario, Canada. Now, I was drawn to the Wave Energy Research Centre for many different reasons, one being the diverse range of expertise and the other being the unique location of the Great Southern Marine Research Facility down in Albany, Western Australia. Albany is known to have extremely large waves. It has one of the largest amounts of wave energy power in the entire world, which makes it a really cool location to study wave energy farms. Now, my PhD specifically is based on a 1-year field study down in Albany where we use drone surveys and stationary cameras to monitor the beach and understand coastal flooding in these large wave energy environments. And this has implications for wave energy farms because at the moment, the coastal impacts of wave energy farms aren't very well understood. So by learning more about coastal flooding in these large wave energy environments helps us take that next step towards understanding the coastal impacts.
Hi, I'm Renan Silva and I'm a final year PhD student at TWA's Wave Energy Research Center. I have a bachelor degree in environmental engineering, obtained in Rio de Janeiro, Brazil, and then I completed a master's degree in coastal engineering at the Delft University of Technology in the Netherlands. My PhD focused on understanding and predicting the impact of submerged structures, such as submerged breakwaters, natural artificial reefs, and bottom-mounted wave energy converters, on waves, currents, and sediment transport. In particular, my research aims to determine if and how submerged structures will result in beach accretion or erosion, and whether it will reduce or increase coastal flooding. I have been using a process-based numerical model for simulating a wide range of wave conditions and structure geometries. The outcome of my research will help the formulation of design guidelines of submerged structures.
Program 2: Wave Device Interaction. Program 2 assesses the behavior of different wave energy technologies in the wave environment. This research informs our understanding of the performance and survivability of wave energy converters in a wide range of environments, as well as determining the optimal constellation of devices in a wave farm. Key elements of this program that can be a step change in the commercial competitiveness of wave energy technologies include numerical models that predict wave conditions and wave device interactions. The following two researchers are part of this program and will explain in further detail.
Hi, my name is Daniel Raj. I'm a third-year PhD researcher at the UWA Wave Energy Research Center. Before joining my PhD at UWA, I completed my bachelor's degree in civil engineering from India, and then I did my master's in ocean engineering from IIT Madras, India, where I continued to work as a project associate for about a year. My research in UWA is about multi-objective optimization of waveforms. Unlike solar and wind farms, when wave energy converters, when they deployed in arrays, they interact with each other through radiated and scattered wave field. These interactions, they enhance or diminish the overall performance of the waveforms. So we need to carefully optimize the location of the waveforms before deploying. To study this, we model a variety of waveforms with different spacing, orientation, and offshore location. Basically, we are looking at the power absorption, reducing the cost, and also looking for any potential coastal impacts, if any. So by doing this, we will be able to optimize the efficient waveform design.
Hi, I'm Toban Traub, a second-year PhD student at the UWA's Wave Energy Research Center. Prior to starting my PhD at UWA, I completed a double major bachelor's degree in mathematics and chemistry in Swaziland. 2 years later, I received a master's degree in mathematics from the University of the Western Cape in Cape Town, South Africa. My current research at UWA is developing a mathematical model for predicting ocean waves as a function of time, a model that runs in real time on a standard computer. This aims at providing a cost-effective strategy for improving the performance of wave power machines. The machines can be tuned relative to the incoming waves when it is known in advance, and this has the potential of improving the power output by a factor of 2. To validate the model, I use time series measurements from wave buoys at Sandpatch in Albany, which is a potential wave development site in Western Australia.
Program 3, Foundation Design. Program 3 analyzes foundation engineering solutions for the specific loading regimes and requirements of the ocean renewable energy industry. The Perth node of the Wave Energy Research Center is home to the National Geotechnical Centrifuge Facility and its state-of-the-art geotechnical centrifuges. Here, a number of scale model foundation designs and loading sequences are tested to provide innovative and cost-effective foundation solutions to the offshore industry. The following researcher is part of this program and will provide further insights.
Hi, my name is Pierre Guvernet, and I'm a second-year PhD student at the University of Western Australia. I completed my master's degree in geotechnical engineering at the École Normale Supérieure in Paris, France, and I am now part of the Center for Offshore Foundation Systems, known as COFS, and also part of the Wave Energy Research Center. So the work done on offshore renewables covers a wide range of research fields, and my research particularly focuses on the geotechnical part, and this has been developing reliable and cost-effective anchoring solutions in order to anchor the coming generations of offshore floating renewables in sand, as this is the typical material that we encounter in shallow water environments. So my research is mostly lab-based. In the National Geotechnical Centrifuge Facility, a cutting-edge laboratory in the basement of the COFS building, we use the centrifuge in order to spin our sample, our scale model, at until 200 times of gravity in order to represent the stress conditions that we have in the field. Also, by using a half model against a perplexed window, we can observe the soil displacement and its failure mechanism that provide really good insight into the soil response at the depths of the anchor.
These three research programs are interlinked, and data from experimental work or numerical modeling from one program flows into the other programs. This holistic surface-to-seabed approach and the rich multidisciplinary talent pool of the Wave Energy Research Center delivers the step-changing innovation needed for Australia's ocean renewable energy sector to become a powerful part of the decarbonizing solutions for our planet. Wave energy has a range of value propositions and applications, not just for systems that connect to electricity grids, but also smaller microgrids and direct end-user supply. The consistent and predictable nature of waves provides us with a huge potential for a clean baseload energy solution to meet global energy needs. Implications beyond energy supply are also coastal protection from erosion, sand accretion, or flooding through the installation of nearshore wave energy devices. Wave energy presents us with an engineering challenge that, like many other challenging research endeavors before, will bring out the best in data science, innovation, and technology developments. In the process of solving the wave energy challenge, we will inevitably make other new discoveries that will benefit our world.